Good afternoon, students. So now we are having interaction for our course of steam power engineering. We have walked for this course for certain distance. We have seen certain concepts. The major part till time what we dealt was related to the thermal cycle of the steam power plant. And we have seen that Rankine cycle is the governing cycle for steam power plant, which has some components: pump, boiler, turbine and condenser. Then, having said this, we went with calculations related to pump, which is a power input machine, work input machine. Then we have gone ahead and calculated for the heat input into the boiler, and then turbine work output and condenser heat loss. So having done these calculations, we could calculate for the work output of the cycle and then efficiency, thermal efficiency of the cycle. With these, we got certain hands-on for the thermal power plant, which is based upon the Rankine cycle. But then we thought that how to improve the output or performance of the power plant. Then we went ahead with certain attachments like reheater. Before that we thought for superheater, then reheater, and then regeneration. So these were the attachments. Accordingly, we calculated different performance parameters for the steam power plant. So this is how till time we had dealt with for the steam power plant subject, and now we will have interaction. Basically, I have got certain questions, and those questions I will try to discuss first. Okay, so this is the steam power engineering. So there are certain questions. First question is, how does basically steam separator works and its types. We will go to the next slide where I will discuss about it. We know that steam separator is a part of boiler and it has different kinds of types based upon the type of application. So here we are seeing on the screen there is a gravity based separation. If the boiler pressure is less than 20 bar, then what would happen, that we have seen that in case of dome on PV diagram, we have seen here in this range there is lot of density difference. At lower pressure there is lot of density difference. At higher pressure density difference is small, and then as we go further high, density difference becomes further small. So since gravity helps us to separate and steam is having low density and liquid water will have higher density, here we will have gravity based separation. So that's where the gravity based separation would work. We will actually the steam vapor plus liquid bubble will try to go up, but since the bubbles will have higher density, it will the droplets, water droplets would have higher density, so it will settle down. So accordingly this steam separator would automatically work. So then we have baffle separation, which is a mechanical separator. So basically we will have steam in water plus vapor mixture into the boiler, and then it will try to go towards the outlet. But in this case the pressure is intermediate, not high and not so low. So there will be a chance that some liquid droplets would also go. So to avoid that, some barricades are made, and those barricades are actually acting as the separators. It's like our in the road we have these barricades. So like that, these are the barricades on the road of the steam to get separated from the liquid water. So this is what we call it as mechanical separation or baffle separation. Now, so we will have third type, which is cyclone separator. So this is cyclone separator, and cyclone separator means actually we are at very high pressure, and since at high pressure the density difference becomes very small. So what will happen, the liquid and vapor mixture will enter into a cyclone, and that cyclone basically is going to whirl, going to rotate the steam which is having liquid and vapor mixture, such that the liquid would get separated and we will have steam which is going up. But again, we don't want to negate the presence of water droplets, so for that we will have mechanical separators, and at the end again, in case of mechanical separator, we will have screens or scrubber. So mainly the use of cyclone as what it is seen here, which is called as cyclone separator. So it works at very high pressure. So first slide. So we will see the next question. So we have seen the question, how is steam separator work? So how is TTD is calculated in numerical in graph? How is temperature calculated from interpolation method? How is temperature calculated in superheat? And how is enthalpy calculated at the point where TTD is given? I will discuss about 2 and 5 first. Let us discuss about 2 and 5. Basically, what do we mean by TTD? So we know that feed water heaters, in case of regeneration, we have steam which is bled from the turbine, and then that steam is used to heat the water which is going to the boiler. So the steam is going from high temperature, high enthalpy to low enthalpy. So this is one type of steam, one type of the feed water heater, and we see here that the steam blade is not changing its phase and water is increasing its temperature. Further, we can see here that if we see the other type of feed water heater, which is having condenser and drain cooler. So here water is increasing its temperature, but the steam initially it changed from dry saturated vapor to liquid saturation liquid state, and then further it got cooled. So there is a drain cooler and then there is a condenser, and this condenser is actually the part of a feed water heater. But if we go ahead, then we might have very high pressure steam led, and that high pressure steam is actually having superheat from the turbine, so it will reduce its superheat and it will become dry saturated in the phase when liquid water is getting heated. Then it will lose its latent heat in the condenser. So this is D superheater, this is condenser, and this is drain cooler. Again in the drain cooler, the liquid steam which was drained from the blade from the turbine will become liquid state, and then that liquid will further get cooled into the drain cooler. So this is what we have seen, that there are certain types. But what is TTD here? So TTD is terminal temperature difference, and that is saturation temperature of the blade steam minus exit temperature of water. So in this case, saturation temperature means T8 and T3 is same. So minus exit temperature of water, which is T7. So this you can see here, it is a positive TTD. Okay. Similarly, saturation temperature is this, exit temperature is this. So we have positive TTD. But now if we come back to the feed water heater, which is at high pressure, so this is the exit temperature and saturation temperature is here. So this is a negative TTD. Okay, so this is how we are having TTD calculation. So for calculation of TTD, we are using the saturation temperature of blade steam, and we will be using exit water temperature. So we will go to the first slide. Now, how TTD is calculated in numerical in graph. So as to answer this question, basically as what we said, it can be calculated based upon two numbers. One is saturation temperature of steam and other number is the exit temperature of the water. But in general, if we are concentrating on what we are trying to do, then in general we would be given with TTD, and if it is not given, we can assume TTD to be 0 degree Celsius. So we can assume TTD and then we can go ahead. So there are two chances in general. In case of the syllabus what we are dealing with, steam power engineering, generally TTD is a very small number, let it be positive or negative, but it would be provided to us in the numericals, or we can assume it at 0 degree Celsius. Then if we know certain temperature of feed water at the exit, then what we can do is, as this question is asked, how to calculate enthalpy. So but the steam table wouldn't have that enthalpy. So in that case, what we should be doing is, the nearest approximation is, we can take the consider this temperature to be saturation temperature of water, liquid water, and corresponding enthalpy we can take. Okay, so this is an assumption. We otherwise need to know certain other parameters or other constant to calculate the temperature of water, but best thing what we can do is, we know from TTD the exit temperature of feed water heater. That exit temperature we will take and use that, consider that temperature as saturation temperature, and then from the temperature part of the steam table we can find out the enthalpy. Then there are two more questions. How is temperature calculated from interpolation method? It is linear interpolation what we are seeing. We can just make T1 plus T2 by 2 or of that kind. That's what I am interpreting this question as. How is temperature calculated in superheat part? In the superheat part, maximum temperature or the amount of, in the example generally amount of superheat will be given, or in the example maximum cycle temperature or turbine temperature at the inlet would be given. So these things would be given, and if not given, then we would have been given certain other things, like we would have been given the amount of heat given in the boiler. So from that amount of heat given, we can calculate the temperature in the superheat part. Since superheat it is simple, we know the suppose enthalpy at the dry saturated vapor, and then we wanted certain enthalpy. So we know that H is the enthalpy in the exit of the superheater. So H minus H saturation is the amount of superheat. So by all means, if we are given with amount of superheat, or we are knowing amount of heat given in the boiler for the superheater, then we can find out enthalpy, which is the at the outlet of the superheater. Once that enthalpy is known to us, we will go in the steam table. We know the pressure, and we will go to the superheat part of the steam table, and in the superheat part of the steam table we will look into the pressure which is of our interest, and then we will scan many temperatures, and we will stop at a temperature in which this enthalpy matches, and that's where we will say that this is our temperature. In case it is not matching, then we will take nearest temperature, or we will find out, we will take two enthalpies, two temperatures, and we will take their interpolation, and then from that we will pick up. But there we might commit certain mistake or certain error, but that is logical. We are assuming it to be in between, so there is no problem. So these were the questions asked by a student. We'll go ahead. So we have seen some set of questions asked by the student. There are certain more questions actually asked, but let me tell, there are certain questions asked about the assignment, question number 8, assignment number 3, or assignment number 4, question number 5, something of that kind. So it looks to have, there are certain issues for the students in sense of getting the marks. So these issues we will resolve in the portrait. So don't worry about that. We will take care for that. Then there are certain questions which were too much practical. There was a question that if a steam power plant breaks down or it has a failure, how much time it takes to get repaired. But how this question has relevance with the syllabus, I fail to understand. However, the top of the head answer for this question would be, it depends upon failure, what kind of failure the steam power plant would have faced. There was one more question, that how would we regulate the power output. So for regulation of power output, we know that we cannot work with pressures, since it's a constant pressure cycle. So pressures are almost pressures are frozen. So what we can do is we can alter the mass flow rate of steam, and by altering mass flow rate of steam we can alter the power output of the power plant. So these were the questions which were asked through the earlier given Excel sheet. There is a question by a student, what is significance of TTD? Basically, TTD is a design element, and then for that we have to know this temperature difference. It's a heat exchanger, basically what we are talking about, feed water heater. So by all means we should be knowing inlet outlet temperatures and all. So for that, TTD happens to be a design point. If TTD is high, TTD is low, across that we can associate it with the temperature, what it would be at the outlet of the feed water heater. But in that sense, it is not a very big design parameter as what we can think about in case of boiler pressure or condenser pressure. But it's one of the elements in case of steam power plant with the regeneration. So there are questions about final exam. The questions whatever are asked and the type of the question what are asked in the assignment, rather that will be continuing in the final exam questions. And then one good point for this online exam at this moment is that you don't have to worry about the data given. The data need not be found out. We will give all the data required for one example to solve, and then there will be certain number of, I would not disclose the required information, but the point is there will be certain number of questions of objective type, where student will have to choose certain objectives. Rather, all questions are objective type, but then there are certain questions which are theoretical type, and then the question can be something of whether reheater can, what is the basic objective of a reheater. Then there can be following options like it increases work output, it decreases work output, it increases efficiency. So certain theoretical questions of this type, and then there will be certain examples based upon Rankine cycle, based upon the components such as turbine. Okay, so but we are practicing ourselves in the tutorials whatever they are given to. So you just have to focus on tutorial. That is more than sufficient. I have got a question. I have a doubt about calculation of enthalpy and specific volume at throat section of the nozzle. So we would be using the equations for enthalpy drop and then velocity, and then accordingly we will be calculating. So for there we will actually focus this when basically we are going to deal. I am having this interaction session mainly for the part till what we have covered. This question I will take it in the before I will not take to next interaction session, it will be too far, but I will answer this question in the portrait. Okay, we will discuss more on a question. It's not a question. Gas turbine problem looks somewhat difficult. Gas turbine problems are more on velocity triangle. Try to understand velocity triangle. And we have discussed velocity triangle in detail in case of gas turbines. So that how to basically how many velocities are involved. A velocity triangle can be how a velocity triangle can be composed. Basically there are three velocities. One is the blade velocity. Okay, one is the steam absolute velocity. So these are two basic velocities, and these two basic velocities would lead to one relative velocity. So one velocity triangle would have these three velocities. But the absolute velocity can be decomposed into parallel and perpendicular components. So that's where we are having whirling component and we are having the axial component. So that's how one velocity triangle would have one more implicit velocity triangle. So there will be 5 velocities related to inlet, and then similarly 5 velocities related to outlet. And then since we are plotting all the velocities at mid height of the blade, we will be having the velocity of the blade same at the inlet and outlet. But then yes, we will again discuss this on the portal. I have taken more questions which were related to steam power plant, thermodynamic cycle, and then components such as boiler and steam separator, these type of questions. But the questions related to nozzle turbine, they would be dealt here onwards. Okay, there is a question, mean heat addition in Rankine cycle. So first thing is, what do we mean by heat addition? Which is the component which is dealt with? Which is a component which is dealt with the heat addition? It is a boiler. So then boiler, what is the mean heat addition in the boiler? So we have certain inlet enthalpy, certain outlet enthalpy for the boiler inlet and boiler outlet. Then that enthalpy difference divided by corresponding entropy difference will give us the temperature, which is mean temperature for heat addition. So that's where the mean temperature of heat addition can be calculated. Okay, basically it is dH is equal to TDS, reversible heat addition. dH is equal to TDS. So dH is known, ds is known, then we can find out T. Whether calculator is allowed in the exam. So these are very exam specific questions. You would get this information through your admit cards or other resources. And if I get such an information, we will obviously pass to the portal. But as I know, calculator would not be allowed. Okay, so the throat question was more on the fact that the pressure was different, get differently found out, and then the steam table has different pressure. Okay, I understand. The question was asked in different sense. The point, there is a delicate point here in case of steam turbines. Basically, we are trying to use the steam table for calculation. And since we are trying to use steam tables, we don't have data for all the pressures and all the temperatures. So we will take always nearest value whatsoever we have and we will go ahead. Okay, so that problem is for you when you are solving the answers or questions on your own. You could see the same fact when you are seeing some solved examples in some books, but you don't have to worry about it when you are trying to work out for the questions for exam, since all the necessary data we would be giving, and we would be giving the nearest value also, so you would be using that. Okay, see, it's an inverse problem. The question is how to find out temperature from the steam extracted from the turbine. So now we know from where steam is extracted. What do we mean by we know? We mean that we know the pressure at which steam is extracted. Since whenever there is a feed water heater, pressure is known. Okay, when we are talking about Rankine cycle has constant pressure heat exchange. Let it be condenser, boiler or feed water. So whenever we are defining steam to be bled from the turbine, so we will be taking the steam from certain pressure. So since we are taking the steam from certain pressure, pressure is known. We know the vertical line of turbine. So from that we know the enthalpy. So we will go back into the steam table. We will find out the pressure. We'll go to the pressure part. We know the enthalpy at that location, and then we will find out corresponding temperature from the steam table. Or best thing is that we can use Moliere chart, and then we will draw a vertical isentropic line for the turbine between two pressures like turbine inlet and turbine outlet, and then at a particular pressure value we will have steam bled. So that pressure line we can find out on the Moliere chart. Wherever that pressure line intersects the turbine vertical line, we will get the temperature directly from TS diagram or enthalpy from HS diagram, and that enthalpy we can use into the steam table and find out the temperature, or we can use that in the TS diagram. We have discussed this. What are the good books for the present course? We can use Steam Power Plant by P.K. Nag. That is a good books, more sufficient for present content of the course. How we okay. So in case of feed water heater, we have always seen that if there is no feed, the question is how to use mass extracted while writing the energy equation. So basically when there is no feed water heater, we just have simple Rankine cycle. Then we have same mass flow rate through the complete circuit, through the complete cycle. That time we always write pump work as H2 minus H1, turbine work as H3 minus H4, or we can actually write boiler heat addition is H3 minus H2. So there we are taking directly enthalpy difference, and those enthalpies are specific enthalpies. So we are actually not considering mass. Basically it is m into specific enthalpy. That will be the amount of heat added or amount of work. That's how we should be calculating. But m is considered to be 1 in complete circuit. But now if we have the feed water heater. Now since we have the feed water heater is taking certain amount of steam from the turbine. So if we consider the feed water heater at high pressure, then some X amount of steam would be bled from the turbine. So that feed water heater, immediately over that we would write X. So then what would happen is, once that X is written, then there onwards, beyond the point of bleeding, just one second, we will draw it in PPT and then we can discuss. Okay. Okay. No problem. So let us try to discuss this point. So this is our Rankine cycle in our TS diagram, and now we are saying that here we had 1, 2, 3 and then 4. Consider ideal cycle with all efficiencies as 1. Now we are bleeding certain steam from here, which is 5. Now since we are bleeding certain steam over here, it will be like this. So we are taking X amount of steam. So here, till here it was 1, but now after here 1 minus X. Since X is a mass fraction which is taken out from the turbine. Now if it is backward cascade, then we will take it here, and that point I will say 6. So the point is, at point 4 we have 1 minus X, and from 4 to 6 we have 1 minus X. At 6 X is coming, so 6 to 1 we have 1. So pump will again have 1 and boiler will also have 1. So this is how we have to work out. Now if we don't have this to be here, and now we have fed it forward. Since we have fed it forward, complete condenser will have 1 minus X mass. Now pump will also have 1 minus X mass. And then we have some point here, suppose 6. So 2 to 6 we have 1 minus X, but at 6 we got X added. So 6 to 1 again we will have 1 mass. And this mass we have to always find out. I will tell you one thing here, just to find out turbine work only for the process 3 to 5, then we will take H3 minus H5. But if I consider this second part of the turbine, which is H5 to H4, then I will not add it as H5 minus H4. Since this has mass 1, but this doesn't have mass 1, so this has 1 minus X. So this is how we have to account this X always, since the cycle has now mass deficit. Mass is not constant. Now coming to heat transfer, what is happening here is, what is happening over here, 2 to some 6 here. We are having steam blade from point 5 till this point, which is 7. So we have X amount of steam which is losing its enthalpy from H5 to H7, and that enthalpy is used to heat the water, which is 1 minus X from H2 to H6, basically H6 to H2. So this is how we are using for heat transfer equation. So we should consider the mass fraction to account for the complete mass balance plus energy balance. So whenever there is this is a flow process. So for flow process we have to account for mass balance also whenever we are dealing with energy. So I hope this is fine. Okay, so I'm not taking questions which are related with gate and the coaching for gate and all. So backward cascade and forward cascade, what is the difference between these two? So the question is this. We have discussed this part in the video. For that I will still repeat that the steam has been bled from the turbine and then it has lost its enthalpy, it has become liquid now, saturation liquid. So now there are two options for us. We can take that steam backward toward the condenser or maybe at low pressure. So that is what we are calling it as steam cascade backward. Okay, so in the case of backward it is very simple. Since the liquid water is at high pressure, condenser or low pressure feed water will be obviously at low pressure. So natural pressure difference exists, so flow can take place. So there is no problem, no attachment is required. And that process we have seen that it is throttling process which is isenthalpic. So that's how that get executed in case of backward cascade. But when we are working with forward cascade, we are saying that there will be a small pump. That pump will rise the pressure of the water which is at the outlet of the feed water heater, and then it will match its pressure either to the high pressure feed water heater or to the boiler and supply it. So there are these two things, what we are calling it as forward cascade or backward cascade. Okay, so what is if supercritical power plants or supercritical power plants run as subcritical power plants? The difference will be there in the boiler. Since we will have two phases present in the subcritical, and then we would have vapor which is immediately getting formed when we cross the critical pressure. So the boiler would have its major difference in case of subcritical and supercritical. But then is there any efficiency limit for thermal power plant? Obviously a number would not appear as something like 80%, something like 60%, but we know there is a limit. We have to always lose heat to get the network output. So accordingly, when we set pressures of pressure of boiler, pressure of condenser and maximum bearable temperature of the turbine, then what would happen is our plant's corner quantities are known to us, and from that we can find out its efficiency. Okay, so first slide. question is about back pressure turbine and brake efficiency. I will have to see that question. I will answer that question in the portal. Question is, in case of combined cycle, heat rejected by topping cycle is equal to heat gain by the bottoming cycle. Actually, this is what the idea is. But in general, in what we can see in the examples what we are dealing with, we are actually using only latent heat of the bottoming cycle to be received from the topping cycle. Okay. So the bottoming cycle would have latent heat rise and amount of heat to be given in the evaporator, so that will be received from the topping cycle. Again, question related to the assignment. I will check with that question and then we will answer those in the portrait. Okay, so thank you very much. We will meet in next interaction session. Best of luck to you all. Stay safe. Take care. Thank you.